So in this video, we are going to talk all about arc length and radians. Okay, so here's what you're going to have to be able to do. You have to understand how to work with the two measures of angles. So in radian and degrees, you have to be able to convert between these two things. We'll also learn this nifty little equation where it involves arc length, which is our A value, our angle, okay, that this has to be measured in radians. So we're already seeing why we need two measurements of angles, and then the radius, r, for a following with this equation. And then we'll have to determine the measures in degrees or radians of all angles that are coterminal with a given angle in standard position, and then within a specified domain. So let's talk quickly about radians versus degrees. So up to this point, you've pretty much only ever dealt with degrees for a degree, or an angle measured in a degree, sorry. So you know it's a measured in a degree with that little unit there. And believe it or not, that is a unit. That's a degree unit. Okay. The problem with this is a unit. It has a unit. So measuring angles using degrees can be an issue because it actually has its own units. Okay, the degree, that little dot there. And when you have units, it becomes tricky multiplying things by certain things and whatnot. So if you're ever an engineer or a scientist or many other fields, you often refer to angles using a unitless measurement. Okay, and this measurement is known as the radian. Okay, so it has no units. It's essentially a scalar. Okay, if you're a physics person. 1 radian is the measure of a central angle subtended in an angle by an arc equal to the length of the radius. So that was a bunch of jibber jabber. You don't really need to know that. It's just important. It can be helpful to know maybe where 1 radian comes from. Okay, so a single radian is if you have 2 radiuses extending, and then you have an arc length. So an arc length is the measure from here to here. And let's say that's equal to the radius. So this is the radius, radius, radius. Well, in degrees, this angle is roughly 57.3 degrees. That's what 1 radian is equal to. Again, this is just helpful to understand where it comes from. Do you actually really need to know that? Not so much. Okay. So let's see how to convert between radians and degrees. So it's important to know how to convert between radians and degrees. The below ratio we'll use to convert between degrees and radians is 180 degrees equals pi. So that's a really useful piece of information. So hopefully you watched the review video. But remember, if we extend this, so far we already can start naming some of our Cartesian plane using radians. So I could also refer to this as pi. Okay. So you might learn many different ways on how to do this. I'll show you a few different ways. Some people like to set up ratios. Some people like to multiply by a conversion factor. I'm a conversion factor type of guy, but if you like setting up ratios, that's cool too. So let's start with 125 degrees. So what we'll do here is I have 125 degrees, and what I'm going to do is I'm going to multiply it by a conversion factor. Now I want my units of degrees to cancel out, so I'm going to put my degrees on the bottom. And then I'll have pi on the top. And from here, you can actually start solving this using some simplification rules. So this will be 125 pi over 180. Now recognize that my units have not disappeared, but they've canceled out. And that's why we put our degrees on the bottom, okay? And then from here, what are both these numbers divisible by? Well, it looks like they're definitely divisible by 5. So 125 divided by 5 gives me 25. 180 divided by 5 gives me 36. And then that would be all that they are divisible by together. So since these things are divisible both by 5, I can simplify. And that will become 25 pi over 36. And there is our solution there. Okay, so that is one way, and this is the way I prefer doing it. But again, is my way the highway? Absolutely not. You can do it many different ways. So I'll show you how to do the conversion over here. So recognize this is not in degrees. This is measured in radian. And you can understand that and recognize that because it doesn't have the degree unit. So here we're converting 3.5 radians to degrees. So what I'll end up doing is I'm going to do 35 multiply, and now in this case I want it to become radians, or sorry, I want it to become degrees. So I'm going to put my degrees on the top, and I can check that because I want my radians to kind of cancel out, so my radians will be on the bottom. And then from there we will end up solving. So this will be 3.5 times 180, and then we're going to get 630 degrees pi, and let's just divide that by pi and round it. So that gives me roughly 201 degrees, and there is what 3.5 radians is equal to. Let's go over here and see what it looks like to convert some actual other types of more fraction type radians. So this isn't radians because there's no degree symbol. So we're going to convert it to degrees. So let's use the same method. I'll have 5 pi over 12, and I'm going to multiply that by that conversion factor. And again, I want it to get the units of degrees. So I'm going to put my degrees on top, and I'm going to try and cancel out my radians. And this is going to work fairly nicely because I get pi over pi, so these guys cancel out. Let's simplify this. So 180 divided by 12. Let's see if that simplifies super nicely. So 180 dividing 12, I don't know if it does. Look at that, it does. So that will be 15 times, or sorry, 5. So we get our 5 here, times 15. And then 5 times 15 gives me 75. So this is 75 degrees. Okay. And then finally, let's do our last example here. So again, we're in radians. So I will take my radians and convert it into degrees. So negative 17 pi over 18. Multiply, I'm going to put my degrees on top and my radians on the bottom. Okay. And I will cancel out my pi's. And from here, 180 dividing 18, well, that's going to give me 10. So I get negative 17 times 10, and this is in degrees. And negative 17 times 10 gives me a negative 170 degrees. So I've converted that radians into degrees. Okay. So let's move on. And again, you might find some different ways to convert these. I'm a conversion table kind of guy, or sorry, conversion factor type of guy, but you could also set it up if you're used to this, where you go 180 degrees over pi equals, and let's say we're trying to get this to turn into degrees. So you would put 5 pi over 12 on the bottom because radians is on the bottom. In this case, degrees is on the top. And you can solve for x here. If you like converting things using this method, you're welcome to. Okay. Recognize you're going to get the exact same thing because you multiply this by this, which is essentially what we've done up here. So the quadrantal angles in radians. So we've talked all about our quadrantal angles. So quadrantal angles are just the coordinate, or the axes that break our quadrants into pieces. So remember, this is known as quadrant 1. Here we have quadrant 2, quadrant 3, and quadrant 4. Okay. And now recognize that we refer to this usually as 0 degrees, 90 degrees, 180 degrees, and then 270 degrees, and 360 degrees once you go all the way around. Well, now we have this new way of representing angles known as the radians. So this would be also 0 radians. This would be pi over 2 radians, pi, 3 pi over 2, and if you go all the way around, it's known as 2 pi. Some useful things to know is this will always have an even number in front on your positive x-axis. So if you go one full rotation around, it's 3 pi. If you go another full rotation around, it's 4 pi. If you go another full rotation around, it's 6 pi. Hopefully you see the pattern here. Over here, on your 180 degrees, it always has an odd number in front. So going around going halfway around would be pi. Going all the way around again, this would become 3 pi. This is 4 pi. 5 pi, 7 pi, so on and so forth. Okay, so not only does 180 degrees equal pi, it's also useful to know that 360 degrees equals 2 pi. Okay, and we'll use this a lot more. Recognize these are useful to memorize, but later on we will learn how a little bit of an easier method to memorize these things. But at the moment, it is best to just kind of memorize them. So in our review video, we found a bunch of information about 497 degrees. We're going to now do that using radians. Okay, so here, use your new understanding of radians to solve the following. So draw 5 pi over 12 in standard position. So first of all, at the moment, we don't have a ton of tools. We're going to gain a ton of tools in the next kind of month here when we learn way more about trigonometry. But at the moment, our toolbox is pretty small. So all I really know in radians that this is 0, this is pi over 2, this is pi, then we have 3 pi over 2, and then 2 pi. Okay, now, so this means I don't really know exactly where it exists in here. So at this point, it might be actually useful to figure out what this number actually equals. Okay, so like 5 pi over 12, let's see what that roughly actually equals in radians. So 5 pi over 12 gives me 1.308. Okay, and understand that this is the exact value, and this is the estimated, or the rough value. So now let's figure out what our quadrantal angles are roughly. So I'm going to do pi over 12. Pi over 2. So this is 1.57. So what does that mean for us? That means that 5 pi over 12 looks like it exists in our first quadrant. Okay, so this is 5 pi over 12 here. So now it wants us to state the principal and the reference angle. Now recall that your principal is essentially your standard angle, and your reference angle is the angle measured to the nearest x-axis. So this one's a little easy because when you exist in quadrant 1, well, your principal angle is your reference angle because the nearest x-axis is the positive x-axis. So in this case, all of these things are the same thing because this isn't going one full rotation around or anything. It's literally just starting from the positive x-axis and you go to 5 pi over 12. So our standard angle, which we'll note as angle S, and our reference angle, which is angle R, these all equal 5 pi over 12. Now, list one positive and one negative coterminal angle with 5 pi over 12. So if you can remember what we did in our other video, and again, if you haven't watched it, please go see it. But what did we do? Well, all we did was we added or subtracted multiples of 360 because we start at that angle and then we go one full rotation around counterclockwise or one full rotation around clockwise. And you can do as many rotations as you want and you'll always end up with a coterminal angle. So here, recall that one full rotation in radians is 2 pi. So this is one full rotation. So what does that mean for us? Well, that means in order to find coterminal angles, we just have to go one full rotation around, starting at 5 pi over 12. So what I'll do is I'll add 2 pi, and then we're going to have to do some simple math here. So adding fractions, remember this is technically over 1. To add fractions, you need common denominators, so I'll multiply this by 12 and this by 12. And I will end up getting 2 times 12, which is 24 pi, over 1 times 12, which is 12. And now you have common denominators, so you can all put it over one denominator. So 5 pi plus 24 pi, since they both have pi's, they are common terms. So 5 plus 24 gives me 29 pi. Okay, and if we were to visualize what that looks like, that will look like this. It'll still be in the same position. Okay. But we started here and then we added one full rotation. So there is our 29 pi over 12. Okay. Let's find a coterminal arm that's negative, and let's go 2 rotations clockwise. Okay, so I'm going to take 5 pi over 12 and I'm going to subtract 2 pi times 4. So in this case, we're going, or well, not 4, let's put that as 2. A little excessive there. So this will be 2 full rotations clockwise. Because it's clockwise because we are subtracting. Okay. So again, we need to do some simple arithmetic here. So I'll do 5 pi over 12 and I'll multiply this 2 and this 2 to give me 4. And now I need common denominators, so this is over 1. So to get common denominators, I multiply this by 12 and this by 12. And this will become 5 pi over 12 minus 4 times 12. Well, that's going to give me 48 pi over 12. And now we have common denominators, so this will be 12 on the bottom, 5 pi minus 48 pi. They both have pi's involved, so they are like terms, therefore we are able to subtract. 5 pi minus 48 pi, well, 5 minus 48 gives me negative 43 pi over 12. So if we were to draw that, again, it's good to visualize what that looks like. Draw our graph, and remember, this is a coterminal arm, so we're still existing just simply right here. But in this case, whoa, let's, there we go. Okay, in this case, we're going clockwise. So we go 1, and then, oh, that did a circle. So we started here, that's 1 rotation, 2 rotations. So this would be negative 43 pi over 12. So hopefully you can see how to find coterminal angles. And this is kind of a hint onto our next one. State all angles coterminal of 5 pi over 12. So this is essentially the general solution. So in order to determine the general solution, well, all we're really doing is we're taking 5 pi over 12 and we're either going clockwise 2 pi or counterclockwise 2 pi or in multiples of that. So we're going to add 2 pi n And remember, n is just going to be any integer. And remember, our integers is represented as z. So this will be -3, -2, -1, 0, 1, 2, 3, 4, so on and so forth. So this would be like 1 full rotation, 2 full rotations, 3 full rotations, and this is all going counterclockwise. And then when you make it a negative, you're going clockwise. So hopefully you're seeing how to work with radians a little bit better. Something you could do to check, some people, and this takes a little bit longer and it becomes a little bit more confusing, but some people like actually just converting this right to degrees, so 180 degrees over pi, and then seeing what that is. So I think we figured out what 5 pi over 12 is up here, right? It's 75 degrees. So this is 75 degrees, which is true. This would be roughly 75 degrees. Okay, and then they obviously just added this. So you could technically turn it into degrees, work with the degrees, and then convert the degrees back into radians, but that does take a little bit more time and adds more steps to possibly add a little bit of extra confusion. But if you become comfortable with working with radians, then you're moving ahead very, very well. Now, I just want to go over the arc length and utilizing its equation. Okay, it's not a super complicated equation, but the questions can get a little bit tricky. Now, for arc length and utilizing its equation, we have this equation. Sorry, brain fart there. So our angle, something to recognize is the angle between the radial lines. Okay, so this is our radius, our radii. Okay, now this angle has to be in radians. Must be in radians. If you do not convert into radians and use this equation, your whole question is going to be wrong. Okay, so let's figure out where the perfect middle of this circle is, and it looks like it's not even a perfect, pretty close to being a pretty perfect circle there. So let's just make this a little bit more clear for everyone. There we go. Okay, and then our middle point is going to be right there. Okay, of course that's not absolute, but we're going to estimate it. There we go. Now, how do we use this equation? So some things to note is you have your radius and you have another radius. Okay, so this is r and this is r. Now what does a represent? A is your arc length. So a would be the length from here to here. So this is your arc length. And then that angle is the angle between the two radii. So this is our two radii. So our angle is from here to here. And that's what this equation is representing. So let's go use this equation and let's find the length of an arc subtended by the angle of 1.3 radians in a circle with the radius of 8 centimeters. So let's draw a really quick looking sketch here. And again, it won't be perfectly accurate, but it's just going to help us visualize what we're doing. So we have our radiuses or radii. Here's 8 centimeters. Here's 8 centimeters. What we're trying to solve for is the arc length here. And this is our question mark. And the angle in radii here is 1.3. So everything we have is r. We also have the radii, the radius, which I said was 8 centimeters. We have the angle, which is in radians of 1.3, and we're trying to find a. So it's as simple as taking this equation, angle equals a over r, and in this case we're solving for a. So what I'm going to do is multiply both sides by r, and I will get r times angle equals a. So this will be 8 centimeters times 1.3, and that becomes 10.4 centimeters. So this is 10.4 centimeters, this length here. Okay. Something I do want to mention is these just have to be in the same units. And that's it. As long as they're in the same units, it will work. So since we had radius in centimeters, our arc length came out in centimeters. So let's quickly look at example 4. So an ant crawled 12 centimeters around a circle having a diameter of 42 centimeters. Determine the angular change of position of the ant to the nearest degree. Okay, so if we draw a rough sketch of this, and our sketch is pretty much always going to be a circle, and then we have our center point there. What's happening here? Well, an ant crawled 12 centimeters around a circle having a diameter of 42 centimeters. So first of all, we can figure out what the radius of this is by simply dividing this by 2. So that gives me 21 centimeters. So it looks like if we started here, so this is our starting position, and this is our finishing position. Okay, and we have our fun little ant here. It's a creepy looking ant, but that's okay. And it says it crawled 12 centimeters. That would be our arc length. So we started here and we went all the way around and finished here. And this would be 12 centimeters. And the diameter of this circle is 21 centimeters. Or sorry, the radius is 21 centimeters. So our R value is 21 centimeters. Now, recognize it wants us to answer to the nearest degree. So we're going to have to do some conversion here, because when we use this equation, so this is our angle equals A over R. When we use this equation, remember, this is now in radians. So let's first figure what this is. So A is 12 centimeters. R is 21 centimeters. So 12 dividing 21 gives us 0.571, and this is radians. So sometimes people will put rad as a shorthand for radians. And now, since it wants it to measure in degrees, we're going to convert. So we're going to take 0.571 radians, and we're going to multiply this to convert it to degrees. So remember, we want our radians to cancel out, so this will be pi radians on the bottom. On the top, it'll be 180 degrees. Our radians cancel nicely, and we will take our values here. So I'll get the exact value. There we go, 0.57142, blah, blah, blah. And we're going to take that answer and multiply it by 180 dividing pi. So that is 32, and it wants us to the nearest degree. So we're actually going to round this up to 33 degrees. And there is how far our little ant went in degrees. Let's look at one more question. A circle has a center O and an arc length DE that is 1/6 its circumference. Determine angle DOE to the nearest degree. So first of all, again, what does it look like? Again, it's a circle. Surprise, surprise. Here is our center, and they noted it as O. Okay. Now, it made an arc length 1/6 of its circumference. Okay. So this thing has some radius, which we'll notate as R, of course. And it went an arc length, which it represented as DE, and DE, or the arc length, is 1/6 of the circumference. So it wants us to figure out the angle made from DOE. So in this case, if this is D to E, the angle made from DOE is this angle here. So it looks like we're simply just figuring out the angle between the two radii. So we can use this equation. So angle equals A over R. Now some things to note is angle A, or sorry, our value A is in terms of circumference. Our value R is in terms of radius, of course. We don't know any of these values, but what we do know is we know the equation for a circumference of a circle. Circumference of a circle is 2 pi r. Now remember, DE here is our A value. The length from D to E is our arc length. So this will be DE over R. We've been told that the arc length is 1/6 of this circumference. So what we're going to do is I'm going to plug in 2 pi r where I see C here. So DE can be in terms of our R values. So this will be 2 pi r. So this becomes 2 dividing 6. Those are both divisible by 2. So this will be 1 over 3 pi r. And now I have my arc length in terms of r, so I can replace it in for DE. And my r values are going to nicely cancel out. So this will become 1 over 3 pi r over r. And as you can hopefully see, our r values nicely cancel, and you're left with pi over 3 equals our angle. And that would be, well, it in radians, but of course it wants us to put it into the nearest degree. So I should actually erase the circle because this is not our final answer. And what we're going to do is we're going to convert to degrees. So that'll be done over here. So pi over 3 times, and remember we want our radians to cancel out, so pi will be on the bottom, 180 degrees will be on top. Pi over pi cancel out, 180 divided by 3 gives us 60, so this is 60 degrees. And that is example 5. So I hope things are making sense. Again, practice a few problems utilizing this equation. If you come across any really difficult problems, let me know. You need any questions answered, come and ask, and try out any assignments that are listed. Have a good day.